give this one a try on your own before you watch this video. I'd like to do this one the real way, or the faster way, but then I want to show you a longer way to do this that you don't really need to do for this problem, but on other problems you may, and I want you to understand how to handle this situation if the question was asking for something else. But let's begin by just solving this the most efficient way. Step one is we're going to draw our picture. So I've got a triangle, x, y, z, with x being the right angle. So x, we'll call this y, we'll call this z, and here's that right angle. Point W is on YZ, where the segment WX is perpendicular. So if I make W, let's put W here. When I connect W to X, this is also going to be a right angle. The length of segment WY is 572, and WX is 429. What is the value of the tan of Z? So the key with this problem is to recognize that this is a similar triangles question. When you have these kinds of right triangles embedded in other right triangles on the SAT, almost always it's similar triangles. So we need to see the tricky part, which sides correspond with which sides. Like we know when we're looking at, let's say, this triangle with the big triangle, we know that this angle equals this angle. So those are corresponding. But when we look at the other two angles, like this one and Z, and this one and this one, which is which? Like which is corresponds with which? It's maybe not clear. So here's what we're going to do. Let's look at the small triangle here and the big triangle here and compare their corresponding angles. We know that they both have a right angle, right? In the small triangle, it's right here. This is angle W, Y, W, X. I'll do that in red. We'll do that in orange, I guess. Right, and that goes with this main right angle for the big triangle. So that's one corresponding congruent pair of congruent angles. What about the other angles? Well, notice in this small triangle and this big triangle, they both share angle Y. So by the reflexive property, Y is congruent to Y. Since they share this angle, that is another pair of congruent corresponding angles. And so now we have the angle-angle theorem of similarity. Once we have two pairs of corresponding congruent angles, or two pairs of congruent corresponding angles, we know these triangles are similar. And so the shortcut on this problem is, if they are similar, notice that this angle X in this small triangle must therefore correspond in the big triangle to this angle Z, because if the orange equals the orange and the black equals itself, right, Y equals Y, then the only way this is going to work out is if X and Z are congruent. As soon as you know two pairs of corresponding angles are congruent, you know the third pair has got to be congruent too, because in each triangle, the three angles have to add up to 180. And if you know they both share two angles, well, they've got to share the third. Otherwise, I don't know, reality doesn't work anymore. So that means if I want the tan of Z, here's a shortcut. I can just get the tan of X. And I have everything I need at this point, because the tangent of X is the opposite over the adjacent. So the tangent of X is going to be the opposite over the adjacent. And when you put that into your calculator, you get 4/3. So if the tangent of X is 4/3, the tangent of Z is 4/3, and that gets us choice D. Now, there is a longer way to do this, which would involve finding the side lengths of the big triangle, and from there, doing your opposite over adjacent with Z. And so while that's not required in this problem, I want to show you how to do that, because, you know, another version of this problem could be, what is the length of XZ? And in that case, we're going to need to use our similar triangles further. So first thing we're going to do is let's find this side right here, YX, XY, because this is a right triangle. And so I can use Pythagorean theorem to find XY. Let's call that little z. Now let's call it C. So 429 squared plus 572 squared is equal to C squared. And I will spare you the arithmetic, but when you put this all into your calculator and square root both sides, you should get 715. Okay, so this is 715. So now what we need to do, let's call this missing side over here, let's call this A, little a. That's what we're trying to find. We need to set up a proportion using our similar triangles to find this value of A. And let's again use our small triangle compared to our big triangle, because now we know which sides correspond to which. So our goal is to find A. So let's use A as part of our proportion, which I'll set up over here. So that side in our big triangle is across from, it's across from the angle Y, the black angle. And so in our small triangle, we have to use the same side across from that angle. So in this case, it's going to be the 429, right? Because this side XW is across from the black angle in the small triangle. And in the big triangle, this side A is across from the big angle, so from the black angle. So these correspond. So I can use them in our proportion. So I can say 429 is to A. Now I need another pair of corresponding sides. What can I use? Well, I have in my small triangle the side across from the red, and I have in my big triangle the side across from the red. So let's use those. Now, on the top of my fraction, before I did the small triangle first, so let's do the small triangle again. The side across from the red is 572. And the side across from the z, therefore, or from the other red angle in the big triangle, would be 715. And now we have a proportion we can solve for A. So we go ahead and solve, and I think we get a kind of weird answer here. It's a weird decimal. So what was it? It was like 563.25, I believe. But let's see. So cross multiply 715 times 429, and then I'll divide it by the 572 to get the A by itself. Oh, 536.25. Okay, close. So that is the value of A. And now, if that was the question you were looking for, you would just put that as the answer. If we wanted to at this point, by Pythagorean theorem, I could find YZ, because it's just going to be 536.25 squared plus 715 squared equals that side squared. But for our problem here, if I wanted to solve it this way, I can now find the tangent of z directly without having to find it via the tangent of x, because I can say that the tangent of z is going to be 715, the opposite, over the adjacent, which is 536.25. We get 1.3 repeating, and that's the same thing if I put 4/3 in the calculator as 4/3. So again, we get choice D. Again, this approach was overkill. We didn't need to do this process of finding that side xz because we had these similar triangles wherein we knew which angles corresponded with which, and then we were able to find the tangent of z by finding the tangent of x, and that was much easier. So don't totally do that if you can find that shortcut. But I wanted to do this long way just in case they gave you a question like this where we need to find these missing sides in these kind of situations where you have right triangles embedded in other right triangles. And the key in those cases is to focus on the angles. The angles are kind of like the ID cards for the various sides of the triangle, right? A side that is across from a certain angle in one triangle corresponds to the side across from the corresponding angle in the other triangle. You can use those as tags, ID tags basically, to know which side goes with which. And so that's why we went through this excursion, just in case. Good to be flexible because you never know what the SAT might throw at you, especially on those hard questions. Either way, we get choice D.